Estimating a phase transition temperature from standard thermodynamic data. So the key to answering this question is, of course, using that old chestnut delta G equals delta H minus T delta S. And realizing that if we are exactly at the boiling point, then delta G is going to be equal to 0 while we're in the process of boiling because we are in equilibrium between, in this case, the liquid and gaseous phase of titanium tetrachloride. So we still have to work out delta H and delta S, and then we can rearrange and solve for delta T. So we're just going to look up in the ALEKS data tab for TiCl4 liquid. Ah. For TiCl4 liquid, the enthalpy of formation equals minus 804.2, and that is in kilojoules per mole. And then the enthalpy of formation for titanium 4 chloride in the gas phase is going to be minus 763.2 kilojoules per mole. And then, because I'm lazy, I'm just going to copy and paste these for the entropy. So that is my standard molar entropy for my liquid and gaseous phase of titanium 4 chloride. So the liquid phase is going to be 252.3, and that is joules per Kelvin. Get the units right, Erin. And then for my standard entropy, molar entropy of my gaseous phase, that's going to be 353.2 joules per Kelvin. So I can calculate delta H and delta S from both of those. So delta H is going to be products minus reactants. So I guess I should have written equilibrium up here somewhere. I forgot to do that. TiCl4 in equilibrium with at the boiling point. TiCl4 gas. There you can visualize that a little bit more then. Okay, so delta H is going to be products minus reactants. So that is going to be minus 763.2 kilojoules per mole minus 804.2 kilojoules per mole. So that is going to come out as plus 41 kilojoules per mole. All right, we're going to do the same to get delta S. So delta S is going to be 353.2 joules per Kelvin minus 257.3 joules per Kelvin, and that's going to come out as equal to 100.9 joules per Kelvin. Okay. So then that shouldn't be kilojoules per mole because I multiplied each of those by 1 mole. Excuse me a moment while I just get rid of that per mole because that is wrong. So now I should be able to rearrange and solve for T. So T is going to equal delta H minus delta G, which we know is going to be 0 over delta S. So that is going to give me delta H. I just got as 41 kilojoules. Oh gosh, hang on, I've got to convert that into joules to make this work. So let's see, 1,000 joules over 1 kilojoule is probably the easiest way to do that. Minus delta G is just going to be minus 0. So make that what you will. And then divided by delta S, which was divided by 100.9 joules Kelvin. So I'm going to get 1 over Kelvin, which is just going to give me an answer in Kelvin. That's nice, isn't it? So that is going to give me, I forgot already. That is going to come out as about 406.34 Kelvin. So then if I subtract off 273.15, that's going to give me my temperature in Celsius. It's going to come out to be about 133 degrees Celsius. All right.